Hello, Markus Völter here. This is a preview of the presentation about a paper I wrote for the ISOLA 2021 conference. Paper is called Programming versus That Things Subject Matter Experts Do or Should Do. And yeah, this is the preview here. The two pictures here on this slide show a slightly biggish crane and a very small one. One of them does the heavy lifting, but the other one, the smaller one, helps the big crane assemble, so there's no heavy lifting without the small crane. So one of the two is the programming people and the other one is the subject matter experts, and you can decide for yourself who is who. I'm not sure actually. It's you can make arguments both directions. So, all right, so introduction. What is the context? Context is that in almost all domains, professional work becomes increasingly dominated by computers and software. We all know that from automotive. I mean, the whole automotive industry is kind of rearranging to become software focused. It happens in healthcare, digital patient records, digital therapeutics apps, stuff like that. In finance, also aerospace, just like automotive, the engineering domains are becoming very much software and knowledge focused also. Law is an example. There's a whole discipline of computational law. I think in medicine and biology, we don't even have to really say, right? I mean, we all know that, the vaccine against corona is kind of dubbed the digital therapeutics, almost like an information theory problem of how to come up with the vaccine. And then, of course, in government, despite all the jokes everybody makes, there is, for example, the Dutch tax agency that does all their tax calculations. I mean, the calculations are always done with computers, but also the specification is done in a very interesting way that's in line with what I'm trying to propose. So the question really is, how does the knowledge and expertise that is currently in the heads of subject matter experts, how does that get into the software packages? So we've been thinking about this for the last year or something, and we created a manifesto, as one does, right? It's called Subject Matter First. You might want to check it out. The core idea of this Subject Matter First manifesto is that software people should build tools, in our case here, domain-specific languages, and execution platforms, and then give these tools, these languages, to the subject matter experts, right? Doctors, tax experts, meteorologists, whatever, who can then use this language to encode their expertise, their knowledge, the subject matter, in a way that is then executable or analyzable, depending on what you want to do, by the software itself. So typically, code generation is then used to transform these specifications, these models, into running software. But that's almost a detail. The key is that the subject matter experts stop writing prose documents or user stories or requirements indoors, which programmers then interpret and potentially misunderstand, and instead directly contribute code to the software, but the code can't be programming language code because that's really not accessible. It's also not efficient. So domain-specific languages promise and have demonstrated significant improvement there. But the question is really, can the subject matter experts do that? Can they use these modeling or specification or call it programming languages to encode their subject matter expertise? So that's what we want to explore a little bit in this talk here. And in particular, we want to look at how is the activity that programmers do, programming, software engineering, different from what the subject matter experts do. And I called it SMEing here, SME, subject matter expert, because I don't know whether I should call it programming or modeling or specifying, because all of these terms have accumulated negative connotations, at least to non-programmers, over the years. And so I'm trying to avoid the bad words, but I couldn't come up with a good word, and so I just call it SMEing. It's also a crap word, but we'll see. So before we look at that, it's probably a good idea to just very briefly recap the high-level architecture of software systems that are built this way. Typically, we build them where the models, that contain the subject matter are generated to what we sometimes call a functional core. It's almost like an engine. It's the core of what the domain does. And that then, of course, still needs to interact with users and databases and storage and stuff like that. So there is, of course, a usually called driver part of the overall system that interacts with the technical world and supplies data to that generated core, that executable representation of the subject matter expressed in the models. And of course, there's generators and IDEs and languages, but I don't want to delve too deep because that's not the focus of this talk. So, differences between the two. I have this table here, and let's explore a little bit what this table wants to show. So on the left, we have a whole bunch of responsibilities and skills that people have or need to have. On the right, we then show to what degree this responsibility or skill is required for software engineers and for subject matter experts. The darker the color, the more relevant it is for that particular audience or group, community. So there is stuff that is very much, software engineer only. Things like developing the languages, the generators, the runtime platforms, the tools, dealing with scalability, performance, security, robustness, availability. These are all classical software and software systems engineering responsibilities. And the subject matter experts really shouldn't care. They just should specify the subject matter in a precise way, and then it's the software people to build software that encodes this in a way, and of course then also to run, build, test, and deploy, and also build the pipelines to automate all of this. So this is really software engineering at the core. The software engineers shouldn't have to understand every little detail of, whatever law or finance rule or automotive aspect this software encodes. Now, there is also the notion of testing, which, of course, on a technical level is done by software engineers, making sure that the actual thing scales or performs or, availables. But the testing the subject matter is not something the software engineers should do. This is something that the subject matter experts should do, which is why this line here is actually green and orange mixed, line number 3. There is also things that are purely responsibility, the responsibility of the subject matter experts. For example, understanding the intricacies of each subject matter instance, of each little detail of the tax law calculation or the healthcare algorithm that you're encoding in your digital therapeutics app. This really is not something a software engineer should care about, but the subject matter expert has to, right? And similarly, determining what is correct in terms of the subject matter, they have to be responsible for the correctness of the knowledge encoded in the system. Again, not something software engineers should do. This is why they, line 3, write these tests. So let's focus on the parts of the SME responsibilities that are kind of gray. So to what degree do subject matter experts have to be able to deal with or understand or work with these kind of classical, semi-classical software programming kind of things, understanding the abstractions of a domain, the notion of values, variables, functions, member access, using arithmetic, comparison, conditional operators, things like parameterization, instantiation, conceptual relationships like specialization, inheritance, subtyping, things like dependencies, modularity, interfaces, cohesion, coupling, and then finally finding and then building new abstractions. This is classical software stuff, right? That's why we have a dark black, dark color on the software engineering side. But to what degree do those those subject matter experts who are not educated as programmers, to what degree do they have to understand these things as well? And you can see it's gray, and it becomes lighter gray, meaning less relevant, the more, if you will, complex it becomes towards the bottom. So let's look at each of those in more detail. So understanding the core abstractions of a domain. Well, obviously that's something the subject matters experts have to do. If you don't understand how to describe your domain, you can't describe your domain. Now, the good thing is it is relatively easy for them to be able to do that because, you know, these abstractions are aligned with the domain. It's their domain, right? So it's usually not a problem to teach subject matter experts, you know, these conceptual building blocks of how to describe tax law or healthcare algorithms. So that's why we have this isometer on the right. How easy is it for these communities to learn or be able to work with this? It's very easy here, green, the bar is on the full right. There is also the need-o-meter that shows how often in how many DSL development projects this particular skill is needed. And obviously it's always needed because if you don't understand the domain, you can't do anything. So, next one, the notion of values, variables, functions, and member access. Isometer, it's not quite as native to the domain itself because it's kind of programmy, but it's reasonably easy to teach. Not a problem usually. People have learned a lot of that in school, but composing functions is a little bit harder. You know, building bigger functionality by, for example, you know, in a functional language, calling functions. Also, member access is initially challenging, and they often prefer, you know, writing, you know, the member of such and such object instead of writing object.member. But that's, of course, bad from an IDE perspective, right? Because you can only do the scoping for the member once you've selected the object. And so it's better to write the member, the object first and then specify the object's member you're interested in. It's kind of unnatural for many people. It's a little bit of a stumbling block, but it's really not a big problem. You do need it almost always. I have not ever seen a DSL without values and variables, and you know, it doesn't have to be called functions, but things into which you pass stuff, then the thing does stuff and you get something out. Is it a box in a data flow diagram, you know, or an actual function? Doesn't matter, but something like that you always have. Next one, using arithmetic, comparison, and conditional operators. You always need it. I've not built a DSL without these. It's a little bit, well, I mean, plus, minus, multiplication, comparison, logical operators is not the problem. But making decisioning, complex decisioning is hard. People don't want to do nested if statements. And honestly, as a programmer, I don't want to do these things. So that's why one thing we've learned is that table notations are great, especially for making complex decisions. So we have in our toolset various forms of decision tables that we use to encode complex decisions in a, you know, reasonable, readable, and understandable way. Now becomes more interesting. Parameterization and instantiation. Not every DSL needs it, right? There's lots of DSLs that can do without that, and that's great. It's also, if you need it, not quite as easy to teach. Function arguments are kind of okay, right? Everybody has, you know, called f of something in school, and the of something were parameters. But instantiating something like objects or other entities which then live independently based on their parameters and can be modified is usually the threshold where like more serious training is needed. And by the way, the fact that training is needed is not an argument not to do it, because in my opinion, the only way to interact reasonably with computers is if you know these things as a professional in basically any domain. Now it becomes even worse, if you will, things like specialization, inheritance, subtyping. Funny thing is, everybody understands intuitively, you know, these things like an eagle is a kind of bird, is an animal, is a living thing, is an object, right? But mapping this inheritance, subtyping kind of hierarchy to these, you know, abstract constructs that are used to describe domains like law or finance or healthcare is often a challenge. People really need to play with this and gain experience. We all know, well, if you're old enough, I certainly know how hard it was for me to initially learn object orientation. It was a bit of magic, right? And so, you know, these things need time to fully grasp, but again, it's needed. Tool support can help. For example, if you can show, you know, all the members of some kind of subtype in the subtype optionally, instead of requiring the user to, you know, in their brain to assemble things, is a big deal. In fact, the whole notion of, running things as opposed to imagining how something will run based on the code you see is very important for subject matter experts, or more generally people who are not too terribly experienced in programming. Now, this one is the worst because things like dependency management, modularity, interfaces, cohesion coupling is used in many DSLs as soon as models, gain a certain size, or you need to you need reuse, but it's hard for many of them. So it's also not really a subject matter concern, right? Yes, in order to not drown in model complexity and dependency chaos, we need to do that, but it's not inherently subject matter. And so this really does require education, training, and often also pair programming, pair specifying between SMEs and more technically minded people. But the good thing is on the other side, on the other side, 95% of the subject matter work can proceed independent of that. So, subject matter experts can work for weeks specifying, their particular, if you will, module and writing tests for it. And then at some point when the bigger model picture is assembled, the more technically minded people have to come into play. And if your DSL tool has reasonable means for refactoring, then it's not that complicated, or shouldn't be, to, modularize things or adding interfaces and stuff like that. So, but this is often, not trying to sugarcoat this, this is the hardest thing to achieve in my experience. Finally, finding and then building new abstractions is really hard. We all know that, right? Software development is about building new abstractions, finding them, and finding the right degree of generalization. And of course, this is what the software engineers do when they build the languages. But it's something that subject matter experts aren't good at, right? They haven't been trained. I always joke that if they would be good at that, they would have migrated into software development by now because it often pays better. But the good thing is it's usually not needed, right? DSLs already contain the relevant abstractions for a domain. It's not the subject matter expert's job to define new ones. I know there is a bit of a gray area, if you define a function, in some sense it's an abstraction, but it's not the subject matter expert's job to, find groundbreaking new ways of describing things. And so it's rarely needed, and in that sense, the fact that it's hard, but it's also rarely needed so there's not really a problem. Okay, so this was the comparison of what people need. Let's look a little bit at the language styles that kind of grow from this. And I have a couple of criteria, again, for, the thinking and mindset of SMEs and developers. I distinguish between notation, things like degrees of freedom, the available amount of creativity, how strictly users want to be guided in terms of what they should or can model or program, generally tool support, how do people generally think about problems, how do they validate what they specify, and then this notion of separating program from data and then running things, program recipe of the running system, blah. And we all know in software engineering, we're perfectly fine with purely text, as long as it's different colors as the notation. Software engineers pride themselves in creatively constructing cool abstracted solutions to problems. They don't need that much guidance. Sure, things like Spring Boot, you press a button, you get the outline or the scaffolding of a Spring application, but it's not at the core of what software developers do. Tool support, yes, it's important, but it's focused on, more or less unguided toolkit kind of free modification of code and models. Also, software people, at least some, accept crappy tools if the abstractions are fine. Thinking about problems. Software engineers, at least experienced ones, they strive for a complete algorithm. Like, solve all problems of that particular class with this, nice, cool program algorithm. Validation, you try out, you write tests, and then you run them automatically. Classical test-driven kind of way. And this notion of separating from program from data, programmers, perfectly okay. We've forever written programs which later run in tests or something. Yes, there is the notion of live programming, but it's a complete niche in software development. So how does this look for subject matter experts? Well, the notation isn't just text. They want tables, they want diagrams, they want, chemical symbols, stuff like that. Yes, also text, but not just text. Degrees of freedom, creativity. They prefer picking from options and selecting alternatives as opposed to creatively constructing. Guidance, very important. There's nothing worse in my experience than giving an SME like an empty file and say, go write your code or model or whatever. They prefer, things that approach forms where there's clearly defined places where they can pick options and put stuff. Tool support, absolutely needed. You don't even have to try without. It needs to be process or use case oriented, so you need to put the right, refactorings or stuff like that into the tool to allow them to execute their particular typical, evolutions of the model. How do they think about problems? Usually as a set of examples, right? So, or as, general case plus exceptions, and that's quite different, and it results in potentially quite different languages or ways of specifying things. How do they validate? They try out, yes, but then they play with it. They want to simulate and then maybe record a particular simulation run to later run it as a, regression test case. And separating program from data is challenging. So the notion of live programming, overlaying values over the code, if you will, is much, much more important for languages targeted at subject matter experts compared to software engineers. Here's another attempt at driving home this thing that notation is really, really crucial. There's a wide variety of notations we've built. The typical graphical, component, how does the data flow kind of notation. Weird but fancy semi-graphical Excel-inspired notation for expressing temporal rules and tachographs. Various tabular ways of describing medical imaging devices and defining their configuration options. Tree-style ways of capturing the calculation logic in text law, plus similarly tree-style ways of expressing tests for those, and language for describing user interfaces and forms and almost like web page layout. So really, notation is totally crucial, as is this notion of live programming, running things, showing previews, letting people play with the abstractions or the models they just created. So where can the subject matter experts learn this? Well, they should learn all of these things at school and university. It's not happening to the degree it should, right? There's lots of ways how you can get through your university education in all kinds of domains, and you never really, you always use Word or Excel and think packages like R or something like that. But really understanding these fundamentals of computational thinking, thinking like a computer, how do you communicate with the computer is not that widespread, unfortunately. I wrote a few years ago something I call Programming Basics, how to think like a programmer, that explains some of these basics really from scratch. There is also HEDI, a gradual programming language that has some of the same goals developed by Feline Hermans. Really, this is how I define computer literacy for professionals. This is how you interact with a computer. It's not typing one word into a Google search box. It's also not hoping that AI will, read your mind. You really have to, unfortunately, to some degree, speak the words of the computer tailored for its use in your domain to be able to competently interact with these more and more dominating machines. So that's it. Thank you very much. And this is where, if this wasn't the video, I'd ask for questions. But for now, I'm just going to press stop and hope you enjoyed this.